All right. Hey, let's get started. Today I was going to continue talking through an example data set in R. This week is intended to be about exploratory data analysis. So making summary pictures, summary statistic calculations, and basic investigation of a data set. Are there missing values? Are there outliers? What kinds of patterns are there in the data big picture before we do more formal statistical analysis? I uploaded a revised version of this script that we saw last time. So the Ldl script, I put a little bit of extra stuff in there this morning. So I recommend that you download the revised version. And I'm going to talk through cluster analysis further today. I started this last time, cluster analysis as an exploratory technique for seeing how individuals or variables can be grouped together. So we'll go through the cluster analysis for the HERS data, and then I'm going to show you also a simulation in R. One of the nice things about R is that it makes it easy for you to generate random numbers and therefore simulate data under a variety of circumstances. So if you can simulate data sets that are qualitatively like those that you're going to be working with, then you can throw all kinds of statistical methods at those simulated data. And since they're simulated, you know a lot about them. You know the true nature of relationships inside those simulated data. So for clustering, for example, this could be viewed as like a black box algorithm for us. We're going to throw a data set into clustering, and it's going to make a picture for us. I mentioned last time that what we do with that picture requires a little bit of familiarity with how those pictures will look under different scenarios. In particular, we'll simulate some data where there are real clusters and see what cluster analysis looks like in those circumstances. We'll also simulate a case where there's no clustering, there's no structure to the data, because you want to be able to recognize, if you do a cluster analysis on some data, you want to be able to recognize when there really is nothing there at all. Clustering is an algorithm, and it will always give you output that is the best way to group things together. But there's no guarantee that that best way is representing something real about the data. The algorithm will always run, but then it's kind of up to you in a qualitative way to decide what to do with the picture. So let's come back to the Ldl data. These come from a clinical trial. So HERS stands for Heart and Estrogen Progestin Study. So these are postmenopausal women. We have 2,763 postmenopausal women, each with existing coronary heart disease. Our population, the people who we are interested in making statements about and learning about, that consists of all the postmenopausal women who currently have CHD. That's the population. We have a sample from that population. Okay. And what we're interested in, or what they were with this clinical trial, was what is the effect of hormone replacement therapy for women in this population. Does it change some of these measures of health, some of these variables that we have that measure health-related outcomes? All right. So we did this last time, but we're going to read in the data. To read in the data, we open up R, and if you're on a Windows machine, you want to go to Change Directory under File. If you're on a Mac, you want to go under the Miscellaneous menu item. But we need to get the working directory pointed in the right place. And Yabo has set us up already. The current working directory, the place where R is looking on the hard drive, is this, which is the folder in which I'm going to be putting all of our data sets. So get it pointing to the right place on your computer, and then you can load the data. Read.csv will go get a comma-delimited text file, load it in as a fancy matrix, what's called a data frame, and we're going to assign it to this object called DTA. So after running this, we're going to have an object in our workspace called DTA. It's a data frame, which means it has rows and columns. Individuals go in the rows, variables go in the columns. Let's load it in, and then three things that you could always do to just quickly get familiar with your data. Look at the dimensions, how many rows, how many columns. Look at the first so many rows, just to take a peek at the data, and then do summary on the data frame, and that'll compute basic summary statistics for each of the variables. So here's the results of running those three things. (2,763) and 37 columns or variables. Our first column is the treatment indicator column. For each of these postmenopausal women with coronary heart disease, were they in the placebo group or the treatment group? We'll talk a little bit later in the semester about how should you design studies. This particular study is called a clinical trial. That's a common mechanism for studying on the basis of data in bio applications, medical applications. Hopefully you're familiar from your STAT 101 or whatever classes in the distinction between an experiment and an observational study. So an observational study is only observing. The study PI collects data, like just find people, ask them things about themselves, a survey or a questionnaire. We're collecting information, but we're not doing anything to manipulate the behavior of the people or rabbits or whatever it is that we're studying. That's observational. And the big problem with observational studies is that while they can tell you about relationships, associations, they can't generally tell you about causation. There's a funny website called Spurious Correlations. Just because you have two variables that when you plot them against each other, they seem to relate with each other, does not mean that one causes the other. And there's all kinds of real-world examples of how you can get into kind of nonsensical conclusions if you don't understand that. So for example, here's one illustration. On the horizontal axis is by year the number of suicides by hanging, strangulation, and suffocation. So here you see that those numbers are increasing from 1999 to 2009. If you also plotted over those same time periods the amount of money that the US has spent on science, they follow each other pretty closely. They are correlated with each other. These are two variables that are correlated with each other, but which you would not expect to have any kind of causation relationship. US spending on science has nothing to do with whether or not somebody's going to commit suicide by hanging. Here's another one where we have number of films that the actor Nicolas Cage was in on the horizontal over time on the black curve, And then the red curve is, over the same time period, the number of swimming pool drownings. And there's a correlation of 0.66. The correlation coefficient between these two variables is relatively high. Number of people who died by becoming tangled in their bed sheets versus per capita cheese consumption. Correlation's very high, 95%. These are all observational studies. We're just observing. So let's go to the year 2000 and observe. Let's write down how many people died by becoming tangled in their bed sheets. And let's write down the per capita cheese consumption for that year. The big issue there is that we haven't tied together those individuals, and we haven't done anything to manipulate, for example, cheese consumption. We're just asking how much cheese did we eat and how many people died by this particular cause. So these are all correlations only, associations only. And in particular, we have no business saying the more cheese you eat, the more deaths from bed sheets you could expect. So the reason I brought that up is because these data come from a randomized experiment. So a clinical trial, that's the kind of experiment that, say, pharmaceutical companies do in order to prove to the government that their drug cures disease and allow them to sell it to you. A clinical trial, an experiment, is where you do manipulate the behavior of the individuals that you're studying. In this case, what they would have done is enroll a bunch of women postmenopausal who currently have CHD. So now we have a big pile of people who constitute our sample. And the way we're going to make it an experiment is to randomly assign, say, half of them to get treatment and half of them to get placebo. Why shouldn't we take our whole pile of people and give them all treatment? Suppose we did that. We have 2,700 postmenopausal women with CHD, and we give them all hormone replacement therapy. Suppose that after 6 months of hormone replacement therapy, let's just pick one of these variables. Suppose their BMI goes down. So the women come in, and every single one of them are given hormone replacement therapy. We watch them for 6 months. They come back in, and their BMI, we check their BMI again. Suppose that at the end of this study, the average BMI has gone down by 2 points or something. What can we say about that? We can only say very limited things about that. If all I do is give everybody the same treatment, then I'm not guarding against the very real possibility of placebo effects. Placebo effects are real, and they're powerful. So there's all kinds of interesting studies, like people who are, there was a study where people were brought in, and some of them were susceptible to poison ivy, and others were not. So poison ivy is a weed that if you get it on your skin, if you're susceptible to it, you get very itchy, weepy rashes. So here's a pile of people, and half of them are known to be susceptible to poison ivy, and the others are known to be not susceptible to poison ivy. Not everybody is affected by it. So people who were susceptible to poison ivy, they were asked to put out their arms, both arms, and on this arm, they were told, we're going to put poison ivy on your arm. But in reality, it was not poison ivy. It was an inert cream. On this arm, not poison ivy, but they were told it was poison ivy. And the majority of them broke out with a rash. And on the other arm, we're going to put something that's an inert cream. But it was really poison ivy. They didn't know it, but the majority of them did not get poison ivy. So there's all kinds of things like that happens very frequently. And that's why when we learn about experimental design, we quickly learn that we need a control group. You need a control group. In this case, suppose we gave everybody hormone replacement therapy And after 6 months, the average BMI had gone down by 2 points. That looks persuasive in favor of the hormone replacement therapy, if our goal is to reduce BMI. But it's completely confounded. You can't tell for sure whether that decrease in average BMI was due to the hormone replacement therapy or just due to the fact that they were in a study. Just the fact that you're in a study, suppose you have cancer and you go to MD Anderson and you're on cancer treatment therapy, just the fact that you're getting a pill that has the chance of curing you can cause you to, have real health benefits. So, clinical trial, and we have a control and a treatment group, placebo and hormone therapy. That's why we have those. I said last time I showed you some tips on accessing individual variables in a data frame. So the age variable, for example, is in the second column of our data set. You can access that in multiple ways. Recognizing data as an array with some number of rows and some number of columns, if you just want the second column, you can do it this way. Or you can specify the name of the column in quotations like this. Or you can use $ to pick out a specific column. Or you can say, with my data frame, name the variable. I'll probably use all 4 of these at one time or another. Our cookbook would tell you more about the use of this kind of thing. So we made a histogram and we made a box plot. Remember, a histogram is binning up the observed values of age and tallying counts, how many women fell in each of the bins. Box plot is a simpler summary of the data. It's just one box. Line in the middle is the median. The outskirts of the box are the 25th and 75th percentiles. All right, I want to do what's called cluster analysis and show you how that can be informative for learning from data. Because we have 2,700 individuals and a bunch of columns, a bunch of variables. We need help turning that huge collection of information into something that our brains can understand and learn from. Cluster analysis is one helpful way to do that. Okay. Before we go down and do cluster analysis, when we did summary of the data, first column was hormone therapy. It's a categorical variable, so summary just tabulates how many times did the 2 possibilities happen. Roughly half and half, treatment and control. Numerical variables, we get summary statistics including mean, median, minimum, and maximum. And then let's look at this variable, drink any. Do you drink? Yes or no? We have 1,680 women who said no and 1,081 who said yes. And apparently we have 2 cases where they left it blank. So no response. That happened over with this variable as well. There were 3 cases of empty response and 3 cases of empty response for poor fair variable. And we need to deal with those before we try to do any calculations, because R will complain when there's empty values. Okay, so if we could go back and talk to the same people, go call them up or send them an email and say, by the way, could you please tell me the value for these variables? That would be ideal. For our purposes, I'm just going to take those missing values, the blank ones, and give it a code that R recognizes as this is a missing value. You can skip this value. So everywhere, let me walk through this code here. Data $drink any. That right there is going to pull to the front of attention the variable drink any. So that one column of data. Remember that square brackets are your way of subsetting a vector or an array in R. In particular, if I take this variable, I want to put NAs everywhere where this variable is blank. And here's how I can ask for, is it blank? Data $drink any, if you want to ask, is the value of that variable equal to something else? That's a Boolean comparison, a true-false comparison. In R, to do that, you use a double equal sign. So if I come over to the console, let's say x is equal to the number 2 and y is equal to the number 1. X double equal y should say no, false, because they're not the same. Is x equal to x? Yes. So true, false. I want to ask for each of the elements of these variables, are you equal to blank? So this right here, if I run just the left-hand portion, it's going to print out all the values of drink any where it was blank. So drink any has 2 blanks. There were 2 blanks. It's hard to see. Let's see. What if I do length? Okay. There are 2 places where it is blank. So this highlights those locations, and then this says put an NA in there instead. So I'm going to do this for all 3 of those variables that had blanks. Now, there are no blanks anymore. No blanks, no blanks, no blanks. Instead of the blanks, they are now NAs, NAs, and NAs. Some of the numerical variables have NAs as well. Weight, BMI, waist, and so on. Here again, if we could go to these individuals and fill in the missing values, that'd be great. For our purposes, I'm just going to get rid of any individuals that have at least 1 missing value. You don't want to throw your data away, if at all possible. Right now, I just want to illustrate cluster analysis, and these NAs are going to cause problems for us. So what I'm going to do here is get rid of any rows that have NAs. You can. R will essentially do what I'm about to do automatically for you. If you say do clustering with the data that has some NAs in it, it's going to drop any rows that have any NAs in them automatically. If you plan, I think it's good practice to go ahead and drop it. Otherwise, you're relying on the software to know what to do with it. And not every function in R will be able to deal with it. Some of them will throw an error. Sorry, we don't work with NAs. So when it's me with a data set, I tend to operate this way. Let's boil it down to the cleanest version of my data that I can get. Try to eliminate any issues downstream as possible by keeping it as clean as possible. Okay. So this, if you're brand new to R, may look intimidating. What it's doing is I want the row indices in which there's at least 1 NA. Suppose that row 5, woman 5, has an NA in the weight measurement. Then I want to write down number 5. And then suppose that woman 11 has 2 missing values. I want to write down number 11 too. Go through all the rows and write down the row numbers that correspond to any missing values. This call right here is going to do that. I don't expect you to know this command just yet, although we will use this kind of thing throughout the semester. So for now, just listen to me talk through it for a second. We'll see it multiple times. This right here would be all the indices, all the row numbers, 1, 2, ... up to however many rows there really are. So take that vector of numbers and then subset it, that's square bracket, subset, and the ones I want to pick out are those that have any missing values. Okay, apply takes your data frame and it applies a function of your choice, either row by row or column by column. Depending on what you put in that argument right there, it's going to apply a function row by row or column by column. If you do question mark apply, it'll fill in the details for you, but putting 1 in this second argument means row by row. So apply to the data frame, row by row, this function. It's a function of some input vector called x. You can call it whatever you want. This is going to be a row. It's going to go row 1, okay, pass that in and apply this to it. Is.na, the row, will be trues and falses, a true or a false for every one of the variables. And if I say any is.na, if there's at least one true, then that's going to turn on true overall. So this is going to give me a true or a false for every single row, depending on whether there's any missing values. If I hang on to the indices where this turns into true, then these will be the row numbers I want to get rid of. So apparently row number 7 has at least one missing value. Here's row 7, and it's got some missing values. Row number 27 also has some, at least one. But everything else, 1, 2, 3, 4, 5, 6, and 8 through 26, and so on, those are all clean, complete records. All right, so now let's turn our data set into the original data, but pull out or exclude all of those rows. Do we have too many rows? How many NAs are there? This one has a lot of NAs, but I don't know that we want these ones with 1 after them. Let's get rid of all these variables that have 1 after them, because we have 2 versions of weight. We have weight and weight 1. And there's a bunch of missing values in weight 1. So I'm going to get rid of all these variables that have 1 at the end. Let's do that. Drop the ... 1 variables. So data gets data. Let's pull out all the column names with these 1s. So I'm going to do data, square brackets, because I want to subset it. I want all the rows for now. And all I'm doing momentarily is getting rid of some of the columns. So I leave this piece blank, comma, which columns do you want? I'm going to say which columns I don't want. By doing the minus, it's going to pull out all the columns I'm about to list. So weight 1, BMI 1, waist 1, WHR1, glucose 1. Anything else? T-col1. And TG1. So this is going to take the whole data set, which includes all the columns, and give back everything but the columns we did not want. Invalid argument. Let's see. Okay, so now we have all the rows and a subset of the columns. And we should have much fewer missing values now. So it looks like 11 or so. So thanks for catching that. Now let's rerun this code. Should be many fewer missing values. Okay, so there's 25 total. And this is going to get rid of all those NAs. All the rows that have any NAs, yank them out of the rows, but keep all the columns. And then let's write down how many rows do we have left. We'll call that the sample size. 2738 is what we're left with. So my sample size, N, we'll call that 2738. All right, cluster analysis. We are going to try to join together or group together either the individuals in terms of numerical variable profiles, or we could also group together the variables in terms of individual profiles. I'll show you both of them. What I'm going to do right now is clustering. I said last time that it's based on distances, like vector distances. Which of the people, which of the women look most alike in terms of these numerical variables? Since I'm going to be doing distance calculations, like Euclidean distances, differences, and arithmetic, you need numerical variables for this application. In particular, clustering, this type of clustering is not applicable to categorical variables. So let's isolate just the numerical variables. That's what I'm doing here. These are the names of the numerical variables. And then I'm going to set aside in data underscore numeric all 2,600 rows, but only the numeric variables. So when I do this, I now just have 12 columns. A bunch of numeric variables. All right. So here's how you can do clustering. We don't have time to go into the mathematical details of cluster analysis or principal components because we have a lot to cover this semester, but I hope to give you a working understanding of them at least. If you want to know more about these topics, you could take a multivariate statistics class, like I teach STAT645, and we go all through it in that class. If you want background reading, I think I posted on eCampus today, there's a book called Introduction to Statistical Learning. And chapter 10, they call it unsupervised learning, cluster analysis and principal components are both examples of unsupervised learning. So there's some basic background in that book, which you can get for free. To do clustering, there's different kinds of clustering, but we're going to do what's called hierarchical clustering. And the starting point for doing that is to take your numerical variables and compute distances. Compute all pairwise distances between variable 1 and variable 2. What's the distance between variable 1 and variable 3? 1 and 4, ... That's row 1. Now do variable 2 with variable 1, variable 2 with 3, 4, and so on. Compute all these distances. It looks like this. Oh, I regret doing that. This, I think I just froze R. Okay. Yeah, I didn't want to do that. I'll show you the distance matrix when we do clustering of the variables. This distance matrix that we just computed would have been 2,600 by 2,600. So trying to print it is not going to go well. But DDIND is all pairwise distances between the individuals. So we are going to use that information to group the individuals together on the basis of their numerical variables. So put together individuals, women whose profiles on these numerical variables are similar to each other. Profiles that are close to each other in like a Euclidean distance sense. I pass in that distance matrix to hclust, and I'm going to save it to an object called HCIND, like hierarchical clustering for individuals. When you do that, there are pieces that come with that output. There's something called merge, something called height, and some other things. I'll show you these in more detail in a moment. But to make a picture and hopefully learn from the results, here is what's called a dendrogram. Okay, so we get a dendrogram that is the tree-like structure on the left. And we talked about this a little bit last time, but every place there's a joint like that represents a grouping, a clustering. Way down at the bottom, there were two individuals who were closest to each other out of all pairs. They were put together initially. And then we reassessed distances and joined the next closest members. And again and again and again and again. All the way up to the case where everybody has been joined together. So hierarchical clustering, you start with the case where every individual is its own cluster. There's nothing that groups them together. And you iteratively work your way up to the other extreme where they're all considered to be one. In terms of understanding what this tells us, we need to make a decision about, are there any clusters? Are there any real clusters in this picture? If so, how many are there? And what's the nature of them? What we're going to look for in terms of asking whether there are clusters or not is the right-hand picture. The right-hand picture, the way I created it was I just plotted height. From the HC output, there's an element called height. And height is this value over at the left in the dendrogram. It is the distance between everything that got put together. Whenever we put this group together with that group, for example, the distance between them was 360 or so. That's what's called also height by R. And in terms of deciding where there are real clusters, you can answer that by envisioning this picture as what's called a scree plot. Think of it like a cliff, and some rocks have fallen off the cliff. Where does the pile of rocks seem to begin? Where does there seem to be a substantive change from going straight down to going across? I'll show you another example in a minute that's a little bit easier to understand. But you're going to make a dendrogram like this picture on the left, and then you can look at the merge heights with a picture like the one on the right, for example, to decide, oh, I think there's 5 clusters there. Suppose we did say that there were 4 clusters. If there are 4 clusters, that would correspond to, in this picture, if we said there were 4, that would be this line right here that goes down, and that group that follows that line down, and that one, and that one. So you would start from the top, and you would take the last 4 merges, the merges that would have given only 4 groups. If we said 5, there would be, or let's say we say 2. If we said 2, then it would be this group that follow that line down and everything else. If we said 3, then it would be this line, this one, and all of these. So let's say 1, 2, 3, let's do 5, 4, 5. I'm going to change this to 5. You can use this function called cutTree. If you give it the output of HC or HClust and say cutTree that object, comma, k equal whatever, it's going to give you back cluster membership for 5 clusters, the topmost 5 clusters. So let me run this and I'll show you what it looks like. HC end cut, just the first 10 observations. HC end cut is cluster membership. If I do table HC end cut, there's 5 clusters. There's 1,881 individuals who were assigned to the first cluster. There's 455 in the second one, 162, 226, and only 14 in the fifth one. If we look at the picture, 1, 2, 3, 4, 5, this is the biggest piece. That segment right there connects all of those. So these would be cluster 1, 1,881 individuals, all grouped together right there. At the other extreme, cluster 5 would be this little segment that goes down to just a handful of points. So there's a cluster that contains 1,900, and there's a cluster that contains only 14. All right, and then here's a helpful picture. To help you interpret those results, okay? So we just said, in some way, you can group these 1,800 people together, and those 14 together, and these 200 together. Let's try to figure out what is the nature of those distinctions. You'll be able to copy this code that I'm giving you here and use it again, but I'm going to say, according to this categorical variable, go through each one of its categories, cluster 1, 2, 3, 4, 5, and for that category, compute the means of all the variables. So compute the means, the column means of our numerical variable data frame, and do it by cluster membership. So when we call this, what we get back is this. At the very top, HC IND cut, colon 1. means this, what follows, is summary statistics, averages for each of our numerical variables inside cluster 1. Here are the averages in cluster 2, 3, 4, 5. And you can quickly visualize all of them together like this. I'm going to draw a picture like this one. So horizontal axis, this is kind of hard to read, sorry, but on the horizontal axis, those tick marks are the variable names. Those are our numerical variable names. Age, weight, BMI, waist, WHR, weight-height ratio, glucose, total cholesterol, LDL, and so on. And there's 5 connected line segments with different colors. The different colors correspond to the different clusters. So we did this thing called cluster analysis, and we found evidence that there surely are clusters. There appears to be bona fide clusters in these data. At least 5, I think it's fair to say. And the nature of the clustering, it appears to have nothing at all to do with these variables. Those aren't driving the clustering at all because they overlap so much. Where the main differences are here and here. So TG and total cholesterol, LDL, and glucose. Those 1, 2, 3, 4 variables are really where the story is in this data set. So this kind of thing can be, informative, revealing about the data set. Is that something you would expect? Go talk to the PI. Does this make sense to you? Why would there be no difference in terms of age and weight and all this? Does that make sense? Hopefully, it fits expectations of the data. Possibly, it tells you something you didn't know about the data or about this population. So maybe you learned something here. Possibly, it reveals problems with your data. If patterns emerge that have nothing at all to do with how the study was designed, then it's possible that these patterns reflect problems, like technical artifacts in the data possibly, or batch effects, or technician differences, things like that. Okay, we are out of time. Let me encourage you on your own time. I'll show you this on Monday briefly, but there's also this clustersim.r script. It's under scripts on eCampus, and it does simulation. So I'm going to generate some fake data, randomly generate some numbers, and I'm going to make up a data set where there are 2 clusters. What does clustering look like when there are 2 clusters? What does clustering look like when there are 2 clusters but they're less separated? The first ones were very easy to separate. And then I did another simulation where they overlap some. It's harder to tell. Then we added more clusters, 5 clusters. What does that look like? And this one's especially interesting, no clusters. So I'm generating random data. This is a randomly generated data from the normal distribution. And the way that I'm generating it, everybody's independent of everybody else. There is no structure at all in the data. In particular, there's no clusters in the data. No row is any more similar to another one than all the others. They're all just their own thing. So run that, see what clustering looks like. So that will help you in practice be able to talk to your PI and say, okay, we did clustering, but I'm sorry, but there's nothing in our data. You need to be able to recognize that. Because it can also, you can always have the clustering picture and try to dig in and over-interpret the picture. First thing you should ask yourself is there anything at all? Because there's no guarantee there's any structure to a data set. All right. Homework's coming this weekend. You'll have all next week to work on it, though. Be reading up on R. Check out that Introduction to Statistical Learning book and the stuff on clustering and principal components. And use the discussion board or shoot me an email if you have other questions, okay? See you Monday.